So I've already created the so tell you what, I'll just do log, what's E, is it E for energy? Okay, so here is a Cobb-Douglas function. Now the problem, of course, is this is gonna not show my output is nice, right? I'm gonna make my table wider. Okay, so let's try that again and see that later. Okay. So, as we look at this model, look at the coefficients. The coefficients should be positive if the marginal products are positive, and we expect that. If people are hiring labor, it's got to have a positive. And so what do we end up? We end up with an insignificant capital coefficient. It's negative, wrong sign, but it's insignificant. Labor is highly significant, and then energy is not, okay? Now, let's just manually add up the coefficients here and just see what they add up to. You got 80 plus 40 is 1.2 minus 0.1, so they add up to about 1.19 or something like that, okay? So what happens if we drop two of the variables? Okay, you don't have to do this in your paper, but you might want to think about it in terms of, I'm just showing you your linearity, yes.
L and Q is the log of...
Q is output, L is labor, K is capital, it's
So it'd be the log of Y there.
yes, I just labeled it Q because I recognize Q as that, okay? And then E is energy use, and L is labor, K is capital, okay. Okay, so let's suppose we drop the other two variables that are insignificant, and then we get a high labor coefficient of 1.42, and so forth. The standard error is large and everything, but we could also get the same thing with let's suppose we just put the log of capital in. Same thing, we get a highly significant coefficient, right? And let's just go ahead and run the whatever you call it, the deck here. Again. So each variable by itself is highly significant, right? The problem is when we put them all in, but again, do you really think output is produced only by energy and no labor and capital? No, we expect them all to be important, right? And again, as I've shown you, there's probably collinearity in this data because if it's a Cobb-Douglas production function, there is necessarily a linear relationship between the inputs, okay? And I showed you that the capital labor ratio is constant in a Cobb-Douglas function when you look at if the firm is engaged in cost minimization or profit maximization, there is a constant capital labor ratio, which means that there's a perfect collinearity. Oops, technically, oh shoot. Let me get this again. Oh, I pulled it out, okay. It should go. So technically, in other words, if this was a deterministic model and there wasn't any error term, there'd be collinearity between capital labor and the energy input automatically, okay? But because, there's probably other things that go into production and there's things that are unmeasured and whatever, measurement error and whatever, we don't get the perfect collinearity. But it obviously has an impact, okay? So, what I suggested is, well, let's test constant, so you can figure out if there's collinearity in the data. I think it should be pretty clear this highly collinear. Now you could look at a correlation and show that, but again, notice you got three variables here, and you're only looking at the simple correlation between two variables. So, but all three are correlated. It's a whole, you can't just look at the simple correlation, but you could look at that and say, okay, yeah, these are probably collinear. Okay, there's no perfect test for collinearity, but this has the classic signs of high R squared and then high and low T statistics and so forth, okay? So suppose instead of looking at the individual coefficients, we want to see if there's constant returns to scale, and I gotta remember if I subtract one. Okay, I think I do that. So now I could just add these up and so forth, but I don't want to test. I want to test the hypothesis against one, because that's the null hypothesis, which is the coefficients add up to one. Okay. You know what? I didn't run that regression. I'm going to run that regression. So it didn't do that because I don't have the regression results with that variable. Okay, now I can do that. Okay, remember I said it added up to about 1.19. So 1.19 minus 1 gives you about 0.19. The t statistic is 1.38. Okay, so what does that tell you? Now again, HO is gamma is equal to 1. HA is gamma not equal to 1. So you get a low t statistic, so what does that mean? Do you reject HO or not reject HO?
A low T?
The t is 1.38. The t is saying how close is this to 1? Reject? Do not reject. Okay. Do not reject HO, and that's because 1.19 is only what? 1.38 standard deviations from 1. Okay? So it's not far enough. The p-value is what? 18%. Using conventional testing methods, the p-value is not low enough. Okay? Or the t-value is not high enough. Okay? So, so the one thing you could suggest is that I don't know what the individual coefficients are for this model. Okay? It's not appropriate to say the labor is the most important coefficient, because the collinearity with the other two variables is just allowing one of them to be significant and the other two to not be significant. Okay? It's by chance. Because you saw how I could make the other variables significant, right? I just dropped the other two, right? Okay? So you can't say energy and capital are not significant coefficients, because it's the labor that's collinear with it that's causing the problems there. So what you could say is, I don't know what the individual coefficients are, but I do know that they add up to a number that I can't be persuaded that they don't add up to 1. In other words, they show constant returns to scale. Okay? Now, the next thing you can do then is say, well, let's suppose we run the regression. Okay, now notice here, this is the unrestricted regression here. So the R squared and the adjusted R squared are there. So suppose I wanted to run the regression and impose the restriction and say, I'm going to force the data to choose the values that minimize the residual sum of squares, but also sets the sum of the coefficients equal to 1. So it's constrained. It's like an optimization problem with a constraint. And that's the constraint of your regression. Okay. Okay, so I need to add a constraint, and my constraint so again, when you add the variables here, you're really adding the coefficients. Okay, so again, this is one of those things where you're going to type in the variable names, but really what it represents is the coefficient for that variable. Okay. So log of labor plus log of capital plus log of energy equals 1, okay? I hit okay. Okay, now I come here and say, well, what constraint do you want to add to your model, Tom? Well, the one I just created, obviously. Okay. And there it is. Ooh, this didn't do a good job. Okay. So now, it turns out energy has the highest coefficient, labor is a lot lower, and then capital is still stubbornly negative, okay? And again, you can check these, they should add up to 1, right? So 72 plus 38 adds up to 110, and then subtract minus 0.10, and so you can add them up, they'll come out exactly 1. Okay? They may, after 5 or 6 decimals, have some change, but the first 3 or 4 digits are going to add up to 1. Okay, now, what you could check on this now is I didn't want to call. Okay, so now okay,